Hi, welcome back to the lectures on Engineering Mathematics 1, and today's we will learn Taylor's polynomial and Taylor series. So, these are the topics we will cover. We will start with the Taylor's polynomial and then coming back to this Taylor series from the Taylor's polynomial and some worked out examples. So, this Taylor's formula, which is a generalization of the mean value theorem or the Cauchy mean value theorem, which we have learned in the last lecture. So, we assume that this function here f has all the derivatives up to the order n plus 1 in some interval which contains the point x is equal to x 0. Having this, we wish to find this polynomial p n x of degree n with the conditions that this polynomial satisfies that p n x, the polynomial at x is equal to 0, is equal to the function value at 0. The second, that the first derivative of this polynomial is equal to the first derivative of the function. The third condition, the second derivative of this polynomial at this point x 0 is equal to the second derivative of the function at the x 0, and so on. So, what we assumed basically that all these derivatives, the function value itself, the first derivative, the second derivative and nth derivative, they all are equal to this derivative of the polynomial. So, having these conditions, what do we expect from such a polynomial? We expect that such a polynomial, if we construct, then this should be close to the function f. Naturally, at x 0 the function value is 0. So, at x 0 and several, so the derivative up to order n are equal, but in general also we expect that because of these conditions that this polynomial of degree n will somehow in some form will represent the function f. So, now the question is how to construct such a polynomial. So, we assume here a general polynomial of degree n. So, we take that p n x is c 0 and c 1 x minus 0, c 2 x minus 0 square, c 3 x minus 0 cube plus c n x minus x 0 n. So, in this special form we have taken this polynomial because of the convenience to evaluate these unknowns c 0, c 1 and c 2, but one can also assume any general polynomial of degree n. So, now we want to find these coefficients here c i's based on the conditions which we have set, or we wish to have that this up to nth order derivative of this polynomial at the point x 0 must be equal to the respective derivatives of the function at the same point x 0. So, having this condition, first we note that the first derivative of this polynomial here is equal to, so once we, this is a constant, so this will be equal to 0, and then we take the second term which will be having here x there. So, we will get this c 1 out of this. Similarly, from here we will get 2 times c 2 and x minus x 0, then we will get here 3 times c 3 and so on. Then if we move further, then the second derivative. So, out of this first derivative we can again differentiate this. So, we will get 2 c 2 here, 3 times 2 into c 3 and so on, and then we can repeat this process further to get the nth order derivative. So, in the nth order derivative, because this was a nth order polynomial, we will get only a constant term which we will see here the factorial n, and the coefficient this c n will come in the expression here, and there will be no x term present because the polynomial was degree n and we have differentiated n times. So, having this, what we get out of the first condition when we substitute, because our condition says the polynomial value at x 0 must be equal to the function value at x 0 and further derivatives up to order n. So, from the functional value we will get here p n x 0 and is equal to all these terms will vanish and we will get only C1. So, P n from the polynomial itself, when we substitute x is equal to x 0, we will get C 0 as P n x 0 and P n x 0 is f n x 0. So, we get the C 0 as f x 0 here. The second, when we substitute in this first derivative, so we will get C 1 as the first derivative of the function, the C 2 again from this condition. So, we will get the second derivative at x 0 divided by this factorial 2 so factorial 2 here, and then the C n will be the nth derivative at x 0 divided by factorial n. So, having these coefficients, now what we have the polynomial. The polynomial says that this P n x will be f x 0, which was C 0 there, and all these coefficients are substituted here. So, this is what we call the Taylor's polynomial of order n. Now, if we go through the example here and construct the Taylor's polynomial of the exponential function, for example, e power x around x is equal to 0. So, the P 0 x, the degree 0 polynomial, only the first term will be present there and e power 0. So, e power 0 will be just 1. So, the polynomial of degree 0 will be simply 1. And if we plot this, so this is the green plot here of the exponential function, and this polynomial of degree 0 is just a constant line. So, the straight line going through this 0 1 point, and if we compute the polynomial of degree 1, so we will get this f x 0 as 1, and then we have the derivative here e power x, the derivative will be e power x, and then at x is equal to 0 this will be again 1. So, we have the polynomial of degree 1 as 1 plus x, which is plotted here. So, it is again a straight line with slope 1, and now if we continue this process, so we can evaluate P 2, then P 3. So, P 3 again we have plotted here with this curve, and then going further. So, we will get like P 5. So, for example, if we plot here P 5, then this P 5, if you see, it is pretty close to the exponential function in a very wide range of or in a wide interval around this point 0, which was the point of this expansion here. And if we move further for the polynomial of degree 6 or 7, then we will be moving closer to the exponential function, and that is the idea of the Taylor's polynomial. So, you can, by increasing the degree of the polynomial, we can approximate our function as good as we like, and we will discuss on these further. So, what is the relation of the Taylor's polynomial and the function? That means, because this Taylor's polynomial were representing the Taylor functions to some approximation. So, now we will denote this R n x as the difference between the values of the given function and the constructed polynomial P n x. So, in this case, what we mean this, that R n x, we define this difference of the function and the polynomial P n x, and in this case now the R n x is called the remainder, because this is the difference between the actual value of the function minus the polynomial value at the point x. So, now the question is the how to evaluate this R n x, and to go further for the evaluation, we first note that the R n at x 0, because f x 0 minus P n x 0, and by construction this polynomial at x 0 is equal to the function value at x 0. So, this is 0, and the first derivative the same thing. So, the first derivative of f at x 0 is equal to the first derivative of the polynomial at x 0. This was the construction of this polynomial. So, all these nth order derivative are equal. So, in this case, therefore, this R n at point x, or the first derivative at point x naught, the nth derivative at point x naught, all are equal to 0. So, we have these conditions or n x. Now, we consider another function here, which is g x, x minus x 0 power n plus 1. So, this function has also the property, if we notice this, that g at x 0 will be 0, in fact the first derivative, because n plus 1 and x minus 0 power n, that will also become 0 at the point x 0, and so on. So, we can continue this differentiation here up to the nth order, and all these derivatives at point x 0 will be 0. So, what condition we have now, that g, the kth order derivative at x 0 is equal to 0 up to the order n, and g n plus 1 is nothing but the factorial n. So, we have here two functions, one is R n x and another one is g x. They have a similar properties here, that all these derivative up to order n, they vanish. So, in this case, if we take the x a point in the interval and suppose that x is bigger than x 0, we can also assume that x is less than x 0, and now we apply the Cauchy mean value theorem for these two functions, the R n function and the g function in this interval x 0 to x. And now remember, what was the Cauchy mean value theorem, that you have this function R n x minus the R n x 0 divided by g x minus g x 0 is equal to their ratio of their derivatives at some point xi 1 and g prime at xi 1. Now, if we notice that R n at x 0 is 0 and also the g at x 0 is 0. So, we have this result that R n x over g x is equal to the ratio of their derivative at some point xi 1 in this interval x 0 and x. We can continue this process. So, further if we apply again the Cauchy mean value theorem for the derivatives R n derivative and g derivative in the interval x 0 and xi 1. So, what we will get? We will get, because these first derivatives are also 0. So, simply we will get this result that R n x divided by g x is equal to the R n, the double derivative over the double derivative of g, now the sum point in between this interval which we have considered from x 0 to xi 1. And now we can continue this process further for the next derivative. So, applying this Cauchy mean value theorem further, what we will get? We can go up to the n plus 1th derivative, because up to nth derivative R n and g both are 0. So, we will end up with this term, and then here this xi n plus 1 lies between x 0 and this xi n, and there was a continuity up to x there. So, what do we get out of this? R n x is equal to this R n, the n plus 1th derivative divided by this g n plus 1, the nth, this here the nth derivative of this g n plus 1th derivative was the factorial n plus 1. So, therefore, this factorial n plus 1 term came here, and then we have this g x, which was the function x minus x 0 power n plus 1, and this xi, which is introduced here xi n plus 1. Now, we have replaced just by xi. It lies somewhere between this x 0 and the point x. So, which is written here, the xi lies between x 0 and x. So, now we note that this R n x, which we have defined, that was the difference between the function f x and p n x. So, if we take the n plus 1th derivative here of this remainder term, the n plus 1th derivative of this f minus the n plus 1th derivative of this p is equal to the n plus 1th derivative of x, because the n plus 1th derivative of n and p n was the polynomial of degree n. So, if we take the n plus 1th derivative, this term will become 0, and we have this R n n plus 1 x is equal to f n plus 1 x. And now, we can substitute in our formula, which was the R n plus 1 here. So, we have substituted now this value of this R n plus 1 as f n plus 1 xi. Well, so Now, we got the polynomial here, which is the remainder term, the R n x, which is the Lagrange form of the remainder. This term we can also rewrite this remainder form in this form. So, this xi which appear there, we have just replaced by this x 0 plus theta x minus x 0. This theta lies from 0 to 1. So, here if theta is close to 0, then this argument here is moving to x naught. When theta goes to 1, this argument here goes to simply x. So, this the argument of this f lies between x 0 and x. So, it has the similar meaning what the other form has. So, we can rewrite this Lagrange form of the remainder in this form as well. The Taylor's theorem or the Taylor's formula, now if we summarize, we have the function f x which can be expanded in this form f x 0, f prime x 0, x minus x 0 up to this nth order term, and plus this remainder term which we have just derived has this form which is called the Lagrange form of the remainder. So, in the special case when we take n is equal to 0, so that means this up to the order 1 we have to write this remainder term. So, we get this f prime xi divided by factorial 1, and then we have this x minus either a or the x 0 whatever we consider. So, then this x the xi lies between this a and x, and in this case we get this form of the Taylor's theorem which was the Lagrange form mean value theorem. So, this is a special case of the mean value theorem which we have seen just by putting n is equal to 0 in this case. Some remarks. So, if we set x 0 is equal to 0, the point of expansion in this Taylor's formula, then it is called the Maclaurin's formula. And in the Taylor's formula, if this remainder goes to 0 as n goes to infinity. So, this is an important remark here. If this remainder goes to 0 as n goes to infinity, then we can write down that Taylor's formula in the form of the series. So, f x 0 and so on, you can continue for infinitely term, and this is called the Taylor series. So, for x is equal to 0, if we set this x 0 is equal to 0, then this is called the Maclaurin series. So, what we have seen this the last remark again. So, it is necessary and sufficient for the convergence of the Taylor's or the Maclaurin series that R n x goes to 0 as n goes to infinity. Because there are examples of smooth functions even. So, smooth means we have the derivatives of whatever order we like, but their Taylor series diverges everywhere other than the point of expansion, because the point of expansion the series will have the value same as the function as per the construction. So, and there are the examples also of the smooth functions whose Taylor series converges to some other function. And for instance, you take this example f x is equal to e power minus 1 over x square and the 0 here. So, x not equal to 0 and x is equal to 0. So, in this case one can easily show that f n x at 0. So, if we take the derivative of this function here e power minus 1 over x square, which I am not doing these calculations, but one can easily compute that all the derivatives of any order of this function at 0 will be 0, and then if we write the Taylor series or rather Maclaurin series around x is equal to 0, then we will get, because all the derivatives are 0. So, we will get 0 plus 0 into x, 0 into x square and so on. And then what we see here, whatever x we keep, the Maclaurin series is giving 0. That means the series converges, whatever x, the series is just the 0, but it does not converge to the function. So, the function was for x not equal to 0 e power minus 1 over x square. So, it is a very simple example where we can see that these Maclaurin or Taylor series, they do not converge to the function. Now, let us just take this example of the Maclaurin series of e power x. Now, again not that. So, whatever derivative we take for this function exponential, it is just the exponential x, and at 0 we have the value 1. So, for all values of n, all the derivatives of this function, exponential function, is 1. So, we can easily write down this Maclaurin's theorem that exponential x is equal to 1 plus x square by factorial 2, all the derivatives are 1, and x n power factorial n plus R n x. So, the R n x is the remainder term, which we have just seen. The remainder term is x minus x 0 power n plus 1 divided by the factorial n plus 1, and the n plus 1 derivative at some point which is x 0 plus theta x minus x 0. So, here if we substitute this x 0 is equal to 0, then we get this remainder x power n divided by factorial n and e power theta x, and theta is between 0 and 1. So, now we will see what happens to this R n x as n goes to infinity. If this is the case, if R n x goes to 0 as n goes to infinity, then we can write down the Maclaurin series of exponential function x. So, here again we note that this is the Maclaurin's theorem. So, if this term goes to 0 as n goes to infinity, in this case we can write down this exponential function as a series. So, we can remove this R n x and then we can continue with the further terms as a series. So, let us just check. So, this is the R n x, the remainder term x power n plus 1 divided by this factorial n plus 1, the exponential theta x, and if we take the absolute value of this remainder term as x power n plus 1 over n plus 1 factorial e power theta x, then we notice that this e power theta x for whatever given x, this will be a finite quantity. So, this will not disturb because there is no n term here. So, if we can now focus on this term, that what will happen when n goes to infinity. We should notice that when n goes to infinity, so this becomes infinity, and here whenever this x is, for example, a large number greater than 1, then this term is also going to infinity. So, we cannot simply say that what will happen to this term when n goes to infinity. So, we have to carefully check this limit, that what will happen to this term when n goes to infinity. So, what we consider for a fixed value of x, we can always, whatever x could be a very large number, but we can find a natural number n such that the absolute value of this x is greater than n. So, whatever x we take here, then this n, the big N, we take greater than the absolute value of this x. Having this, we will also consider one more n, the small n term which is appearing there in the formula. So, which is bigger than this number n as well. Now, we consider this term modulus x power n plus 1 over factorial n plus 1. This factorial n plus 1 is the product of n plus 1 n up to 1, and we have here modulus x power n plus 1. So, we can write down in the form of the product as, so factorial x divided by 1, factorial x again divided by 2, and so on. We can continue. Now, just look at this term here, which have appear after this n minus 1 terms. So, modulus x divided by n, here also this absolute value x divided by n plus 1, and so on. So, this term here, absolute value of x divided by n. So, out of this expression, what we see, the absolute value of x divided by this n is less than 1. And now, if we assume this as a number q, so we have a q here, and this is in fact divided by n plus 1. So, this is less than q, and all other terms here are less than q. So, again you note that this n was bigger than n. So, we have gone up to this n plus 1 term. So, this with this n will be somewhere in the middle. And now, this q what we have noticed, because the absolute value of x divided by n is less than 1. So, what we see now, we can replace this equality by the inequality. So, less than equal to, because here we have replaced by q and this one is also replaced by q, though it is less than q, this is also less than q, all these terms are less than q. So, now how many q's we have here? So, n minus 1 terms are already there and then the total terms were n plus 1. So, if we can rewrite now the total term n plus 1 and already these terms are n minus 1. So, n plus 1 minus n minus 1. So, this number here is n minus n and minus 2 and modulus s n minus 1 over factorial n minus 1. And now, we can take a limit here in this case and q is less than 1, and when n goes to infinity. So, this n goes to infinity, this n here it goes to infinity and q is less than 1, then this goes to 0 and here some fixed number is appearing. So, this everything goes to 0. So, this absolute value of this remainder term which goes to 0. So, what we have seen that this remainder term which was a part of the remainder term is less than a term which goes to 0 as n goes to infinity, and we can conclude that the remainder goes to 0. So, these are the references which were used for preparing these lectures and the conclusions. So, what we have learned today is the Taylor's formula, and very important topic in the differential calculus. So, a function which is smooth enough, we can write down as f x 0, f derivative x 0, x minus x 0 and so on, plus this R n x term which is called the remainder term, and this is one form of the remainder term f power the nth plus 1 derivative divided by n plus 1 at factorial x minus x 0 n plus 1. And what we call this, the polynomial term we call the Taylor's polynomial, the whole result this is called the Taylor's formula. And then we have also observed that when R n the remainder term goes to 0 as n goes to infinity, then we can write down this Taylor's formula as in the terms of a series which is called the Taylor series. So, that is all. Thank you for your attention.